Hello and welcome to a math series for teachers in the FET phase and of course everyone else who's interested in education in the country. Let's take a look at our video. In this lesson, we'll look at the inverse of trigonometric functions. Learners' prior knowledge of algebraic inverse functions and normal trigonometric functions is used to get the concepts across. Inverse functions are important in mathematics because they form a big part of relationships. Just as in algebra, trigonometric inverse functions can be represented in the form of a graph. The intended outcomes for this lesson are to review the inverse of familiar functions and standard trigonometric functions, to draw graphs of inverse trigonometric functions, and to look at the properties of graphs of these functions. The teacher first reviews the learner's knowledge of normal trigonometric functions. They will need this knowledge to understand inverse trigonometric functions.
What is the amplitude of this graph? What is the amplitude of the cosine function?
The amplitude is 1.
The amplitude is 1. What is the period of this cosine graph?
The period is 360 degrees.
The period is 360 degrees. And just by way of recall, don't forget that the value in front of the cos indicates to us the amplitude, the A value. The value in front of the theta would indicate to us the B value. And to determine the period, we say 360 degrees divided by the value in front of theta, 1.
Just taking a little step forward,
360
and
divided by
it's
1
very
is
useful because it reinforces their
360.
understanding.
Thank you.
The learners will have done algebraic functions and they would have looked at inverse functions. So the definition to me of a function is like if it's a function tells you a relationship that you can move from here to there and you need to be able to go back. So if trigonometric functions, they are functions, they need to have an inverse.
The teacher now reviews the idea of inverse functions through carefully directed questions, making sure the concept is well understood by the learners.
What do we mean by inverse?
When we're talking about the inverse function, we mean that we replace the x's with the y's.
Replace the x's with the? So wherever I see an x, I'm going to replace it with a y. Wherever I see a y, I'm going to replace it with an x. That's what it looks like. So that would be my inverse.
So the function y equals x plus 1 becomes x equals y plus 1, which can also be written as y equals x minus 1.
Here we have the function y is equal to x plus 1. When we change all the x's to y's and the y's to x's, what we basically have is a line y is equal to x. A 45-degree line running through the origin, and everything is reflected around this line. Notice what happens. The y-intercept here becomes an x-intercept there. An x-intercept here becomes a y-intercept there. It's as though we placed a mirror along the line y is equal to x. Now you may be already wondering, if this is what a straight line looks like, can we imagine what's going to happen to a cos function if we do that?
The teacher now establishes that when a function is inverted, the degrees and units are swapped between the x and y axes.
Let's change in the inverse function all the x's into y's and y's into x's. Now, what would you now have along your x-axis?
You have units now.
You will have
Units.
Excellent. We'll have units along the x-axis. What will we have along the y-axis?
Degrees.
That's what's going to happen to my axis. And we need to understand what's going to happen to the axis in order for us to do what? To be able to draw the inverse graph. First thing, we need to establish what does the inverse function look like in its algebraic form. We know y
The algebraic formulation for an inverse trig function works like this.
or we prefer to write it
The inverse of y equals sine x is x equals sine y. This can also be written in the following two ways. Both of these notations are read as arc sine
Let's just
x.
do that and see what happens.
In the case of the cos function, y equals cos x, the inverse is arc cos x. Arc cos x can be written in one of these two ways. The notation f to the power minus 1 is unfortunate because we also use it to indicate powers or reciprocals, where f to the power minus 1 is equal to 1 over f. So it is important to keep in mind that when we write arc sine, we mean the inverse function and not the reciprocal. The learners are given worksheets complete with a table. The x values are given. They will need to determine the values for arc sine and then draw the graph.
How would we go about doing this? You are given x values. How would you go about finding the corresponding y values? Anyone like to help us with that? Yes, Princess?
We'll use the calculator.
We'll use the calculator. Okay, which key of the calculator are we going to now use? Yes?
You first by pressing on the calculator second function and then go to sine and then press the units as values. Yes.
Well done. Has everybody got that? Yeah, okay. So let's do that now. Just make a note.
We should note that mathematically, the inverse of a function must also be a function. Because all the trigonometric functions are many to one functions, the inverse will be one to many, and therefore not a function. We therefore have to restrict the domain of the function so that its inverse will be a function. In the case of y equals sine x, we restrict the domain to the interval minus 90 degrees to 90 degrees. We call this the principal values of the function, and our graphs therefore look like this.
So working together as a group has its benefits. They're able to share their ideas in the groups. They're able to discuss and compare answers. They're not copying. It might seem as though they're copying answers down, but no, they're actually sharing the information. And that strengthens their knowledge. It also, those that are weak in the group, basically piggyback on others. But in that piggybacking situation, they're learning because they realize where they made their mistakes and they're able to pick up information and say, okay, I've made my mistake, I need to correct it. And within the group as well, peer teaching takes place.
The teacher now recaps what the learners have just done. He starts off by showing the standard sine graph between 0 and 90 degrees.
All the x's, y's, and all the y's, x's, what am I going to do to this graph? I'm going to turn it around, correct? But this still does not look like your graph. You know why? All we've done is a 90-degree rotation. Remember that the inverse function is a complete 180-degree reflection. So based on that, what I have is if I turn this around, which won't be very good here, if I turn this around, this is what it should look like. And there's a complete reflection of the sine graph which you have on your table right now. So it does a complete reflection in the line y is equal to x. For this particular function, what we are going to do is this. Our principal values are going to be defined between 0 degrees and 180 degrees.
The learners will now repeat the earlier activity, but apply to the cosine function.
So let's proceed. Remember, we are now working with arc cos. So can someone tell me which key am I going to press on my calculator? Yes?
Second function, cos, and the unit.
Second function, cos, and the unit or the x value given to me. Again, remember to round off your answer to a full degree. Okay, you may continue.
The teacher goes around the classroom, listening and observing the learners working in groups.
I think where we are using the issue of discovery, even though we brought in the known, the kids are going to discover something new for themselves. And it's best, rather than me as a teacher standing in front and telling them where to find the points, how to use the information, it's better for them to interpret it, then it becomes meaningful to them. They found the values.
When recapping, the teacher again starts with the ordinary cosine function, represented between 0 and 180 degrees. As with the previous example, a 180-degree rotation is needed to create the inverse function.
I tell myself I've replaced the x and the y-axis, I've changed them around. I need now to reflect this. If I turn it around, this is what it should look like, taking this shape here. You know, we've changed the x-axis to the y. Oh, that's what we've said. We've just swapped axes around. But tell me, what is the domain of the function y is equal to arc cos x?
From 0 to 180 degrees.
From 0 to 180 degrees. Let's go back. What do we see on the x-axis? Do we see degrees on the x-axis?
The teacher recaps the important elements of the lesson. The x-axis is now measured in units and the y-axis in degrees. What is the domain has become the range and vice versa. And the inverse of a graph is a reflection along the line y equals x.
The range here, which we have taken from negative 90 to positive 90, is because of the definition. The principal values given for the function y equal to arc sine x is between negative 90 and positive 90.
The lesson becomes much easier if we can actually show learners how it relates to every day. You know, they see the need for that topic. But really in algebra, in trigonometry, I feel to get a good example for this level. And it might make it difficult, but because they have already an understanding of inverse from algebra, I don't think it's that problematic.
I'm now going to leave you with a challenge, and I want you to investigate on your own.
The teacher finally gives the learners some questions to investigate for homework. The learners have to determine what would happen to a function y equals a arc sine x if a is given a value other than 1, for instance of y equals 2 arc sine x.
In other words, I've given it an a value other than 1. What I wanted them to really find out and to discover is that there is a relationship between inverse functions, and they extend across the curriculum. Very often we confine inverse functions to the grade 12 higher grade syllabus. It's algebra. So they don't see inverse trig functions ever. And we've exposed these learners to the fact that inverse trig functions do exist, and you can draw them.
Now that we've seen our video, it's time for us to welcome our guests. Smangaliso Twala, who's an independent maths consultant, Catherine Hunter, also an independent maths consultant, and Taska Matlejwane from Pafokgang Secondary School. The first question, starting with you, Catherine, do you think it is useful to relate inverse trig functions to other inverse functions, as it happens here in the video?
I think so, and I think perhaps not enough emphasis was given. And in this particular case, I think not a very good example was given. They showed a straight line graph, reflected it in the line x equals y, and showed that that was the effect of the inverse. And I think that in fact that same idea could have been applied to quite a few more graphs to leave the lasting impression with learners that this is what the effect of drawing the inverse graph is, before they relate it to trig functions. Because in fact the trig graphs are S-shaped. They're very awkward to just imagine, for example, rotating through 180 degrees or reflecting through a line of symmetry. And so the understanding of what a graph looks like when it's reflected needs to be very firmly in place in the minds of the learners before they face trigonometric functions. So I think that yes, it's absolutely fundamental that other functions are treated in the same way before trigs are introduced.
Okay, Smangalisa, you seem to agree on that one.
Yes, I do agree. I think the teachers should have done a lot on inverses first. And I was just looking at the whole thing and saw an opportunity for the teacher maybe to actually bring a real mirror in the classroom, to actually put on those functions that the children have already done, and then see what is actually happening, what the graph would look like on a mirror, and maybe try and trace that before maybe coming on to the inverses themselves and maybe writing them out.
Taska?
Yeah, it is true. He should have indicated that there are quite a good number of other reflections, but particularly the reflection along the line of y equals to x is the one that which is an inverse. And however, not only to show a straight line which will be parallel only, show even at least one line that which they will intersect where the mirror is supposed to stand along the line of y equals to x. And from there it will give him a good basis of saying the reflections are going in a particular line. I think he did not really use all the resources available.
Okay, and what problems does this topic hold for learners, and how should teachers help them through that?
It has challenges, especially when you come to trigonometry in particular, because you know these learners, firstly, the notation. It's important to acquaint themselves with the notation. Let me just take a notation whereby they say y equals to arc sine x, or y equals to sine x to the power -1. And they should be told that it is not the same as 1 over sine x, because they are coming from algebra, where they would say x raised to power -1 is the same thing as 1 over x. But in this case, it's not the same. Now, that difference, I think it needs to be much more emphasized. It can bring a lot of unhappiness later.
Range and domain, are they useful concepts in this context?
Children have got to know what the range is and what the domain is, because then this determines how big their graph is going to be and so on, whether it's going to go to 360 or it's 180 and so on. So it's very important that children should know these concepts.
Catherine?
I really liked the way that this teacher revised the meanings of those words and others. But I think that he just asked, he threw out the question to the class, what is the range? I think that was one of the questions, and what is the something else? And in fact, he could have referred to the diagrams that he had on his overhead projector. I think that he used the overhead projector wonderfully, because it was a good illustration of how you can just turn the graph around 180 degrees or flip the whole diagram upside down. But he could have added to that to show what in fact happens to the domain and the range in the case of an inverse. He would have been able to very easily do that using the overhead projector. And I think that it is something, it was a bit lacking in this video.
Okay.
Yeah, the concept of the domain and the range, he could have also used it to go back to say, how do you assess that if a graph is a function, like the vertical line testing method, and then throw in the whole graph as the inverse of a sine, which will be going the other way around, and ask the learners if that is a function or not a function. Upon them discovering that it's not a function, they will realize that they should cut out somewhere. And now it will bring in nicely a concept of within what range is this a function? And hence it'll now come up with, say, is a function or not.
Oh, okay. Smangalisa, the learners, do you think they were active enough during the lesson?
No, I wouldn't say so.
Why?
To my observation, most of the work was mostly done by the teacher asking questions, and the learners were just answering routine questions. And I would have liked to see the children actually being given a problem. And maybe, like Catherine was saying, that maybe they have to look into this particular problem when you're doing its inverse. What is the range, what is the domain, and so on. Let them do that on their own, And maybe also bring in the issue of the mirror, which I like, of course, for them to be able to see the mirror image of the functions that they had done already in previous years or in previous lessons. So that now they can see the different inverses. Now, in this case, they were just going ahead with what the teacher was doing, but not too much involved or enough involved in the lesson.
Catherine?
I would have liked to have seen more examples of learners actually plotting points that arose from the original function and of its inverse as well, and making sure that they understood that yes, you can flip over the graph if you like, but that coincides with what would happen were you to plot the points bit by bit along the line. It may be that the teacher was able to assume that the learners did make that connection, but I think it's worth reinforcing anyway that, in the same way in which we've stated in other videos before this one, that it's important that the understanding is not lost, and that whatever the fundamental knowledge is that the learners have must be drawn on, must be reinforced and summarized throughout. We don't want them to take a leap of faith and just think, well, if we turn it this way, that's the inverse and so on. We need to go back to basics and make sure that they really hold on to where those points on the line come from.
Taska?
Yes, in addition to what my colleagues have said, I would say the very transparency. I think they should have been used more by learners as the teacher was checking from group to group. That had a potential of groups working together very, very closely, showing them, how those things reflect and so on. And also maybe they could have highlighted also the question of saying why ultimately finding it that it should be a reflection over 180 degrees. Maybe remind them of the properties of a mirror. That's why we say it's a reflection. That will marry well with other subjects like science, which will be cross-curriculating.
So you feel the learners could have been more actively involved in that way?
Exactly.
Any other issues you'd like to raise?
The notation is very important. It normally baffles students. They don't know what a reciprocal is and what an inverse is. Where is the difference? Because at some stage, the inverse and the reciprocal, when you're talking basic algebra grade 8, tend to be set in a similar way by educators. But later on now, it starts to differ. Therefore, those differences need to be strongly highlighted.
Okay. Catherine, any other issues from your side?
I think it was a very interesting lesson, and it draws together lots of topics that the learners would have had contact with in the past. For example, the issue of symmetry and using a mirror and so on. And applying that to trigonometry, again, would give them the opportunity to believe that they can understand it and that they do have the prior knowledge that is needed. It's an intimidating subject, and anything to do with shifting graphs, reflecting graphs, rotating graphs, and so on, it's quite a difficult conceptual concept for learners. And whatever leg up you can give them to support that, I think is very important. As the teacher stated in an earlier video, trigonometry is an interesting marriage between algebra and geometry. And this particular lesson shows that point very strongly.
And that's all we have time for this lesson. Thank you very much for joining us. And thank you to our viewers at home and at schools for joining us. Goodbye.